Hi, today I'm going to talk about kinodynamic motion planning for multi-legged robot jumping via mixed integer convex program. The ability to perform dynamic motions such as leaping over gaps and jumping on high platforms is a unique advantage of legged systems. Our goal is to develop an algorithm to generate dynamic trajectories for multi-legged robots to traverse challenging terrains. This problem could be formulated as an optimization problem where the goal is to reach the goal region as well as satisfying the following constraints, which includes the robot dynamics, foothold choices, and so on. In this specific case, the control constraint is the torque limit constraint, which involves a mapping of the ground direction force to the joint space through the Jacobian matrix. This problem is a difficult problem to solve because of the non-convexity from the robot dynamics as well as the control constraint. The non-convexity of the robot dynamics comes from the bilinear term R cross F, where R is the vector from the center of mass of the robot to the contact point, and F is the ground direction force. The non-convexity of the control constraint comes from the trigonometric terms in the Jacobian matrix. To tackle this problem, we propose the following approach. First, we use linear dynamics model and the feasible range polytope to somehow push the non-convexity from the robot dynamics to the control constraint. Then we apply mixed integer convex relaxation to formulate a mixed integer convex program. We make a series of mild assumptions to alleviate the curse of dimensionality associated with mixed integer program. The motivation for formulating an MICP is that first, it provides a global solution to a given grid resolution, and second, there's no need to supply any initial guesses. And third, many of the shelf solvers are available for solving an MICP. Assuming the legs are massless, we can simplify the robot as a 2D single rigid body. The dynamic model is that the second derivative of the configuration of the robot is equal to the inertial tensor inverse times the spatial range plus the gravitational acceleration. The spatial range trajectory is parameterized by the Bezier polynomial, and because of the linear dynamic model, given the initial conditions, the state trajectories could be obtained by linear operations, and the constraints could be imposed at the sample points. The notion of feasible range polytope is used in this work for more condensed representation of the constraints. The feasible range polytope is the intersection of the contact range cone and the actuation range polytope. The CWC encodes the friction cone constraint, and the AWP encodes the actuation constraint. The feasible range polytope of one leg includes the force term as well as the moment term. The FWP of two legs is the Minkowski sum of the FWP at each of the contact leg. The Minkowski sum of two sets is defined as follows. Here we provide a visualization of the FWP. As we can see in the lower left graph, the FWP of each contact leg is a two-dimensional polytope. When the robot is in double stance, the FWP is a three-dimensional polytope, as could be seen on the right-hand side. By using the feasible range polytope formulation, we can transcribe the original formulation with complex dynamics and complex constraint into a new formulation with simple linear dynamics and complex yet condensed constraint. The FWP constraint is still non-convex, but we can formulate a mixed integer relaxation by discretizing the configuration space of the robot. The non-convex configuration space of the robot is discretized into tetrahedrons, where each tetrahedron is represented by a set of linear inequality constraints. By making the following assumptions, we can segment the C-space of the robot into three regions, each region corresponding to a unique stance mode. This implies that each configuration of the robot corresponds to a unique stance mode, and the contact scheduling is baked into the state trajectory Q of t. The configuration space discretization allows the originally non-convex range constraint to be imposed as a mixed integer constraint. a binary matrix B is introduced such that when Bij is equal to 1, the following linear constraints are activated. The first set of linear inequality constraints says the configuration of the robot at time ti resides within the cells J. The second set of linear constraints activate the FWP constraint associated with the cell J. Additional constraints are imposed for physical feasibility, where the summation of the matrix B along the J dimension is always equal to 1. This means that at any time Ti, the configuration of the robot could only be within one of the cells. Other mixed integer constraints are also imposed to formulate the MICP. For the flight kinematics, there is bilinear term, which is the product of terminal velocity at the end of the stance phase and the aerial time. We use the McCormick envelope approximation as the mixed integer convex relaxation for the original bilinear term. For the foothold position choice, we segment the terrain into piecewise affine function and introduce additional binary variables for each segment of the terrain to determine the touchdown position. By solving the mixed integer program, we can obtain the control and the state trajectories, which can then be applied on a hardware platform. Experiment results suggest that the trajectory generated by the MICP could enable the robot to jump on platform that is 80% of the robot height. More complex behavior could be achieved by solving the MICP. In this case, the robot wants to reach the goal region on the right-hand side. However, it cannot reach the goal region within a single jump because of the torque limit constraint. Without any supply of initial gases, this algorithm figures out the strategy to use the platform on the left-hand side as a stepping stone towards the goal region on the high platform. One of the potential applications of the mixed integer formulation is to generate a trajectory that could be used to warm start a full-scale trajectory optimization. Thank you for your attention.